Everyone, this is Z here, and today we are going to be talking about Boyles Law. So we're going to cut to our PowerPoint and get started. Boyles Law is a law that relates the pressure and the volume of a gas. So who was this guy, Robert Boyle? Robert Boyle lived in the 1600s, so we're looking at a time, the same sort of time as Sir Isaac Newton, and it was a time when scientists were first beginning to actually experiment rather than just to make stuff up by thinking about it. He has very famous, Robert Boyle had a very famous book published called The Skeptical Chemist. He published in 1661. He was a founding member of the Royal Society, which is still going. It's a society of practicing scientists. And he's really regarded as the first modern chemist and is considered to be the founder of modern chemistry. In fact, he hired Robert Hooke just as an assistant in his experiments on air pressure. And you'll notice he also has an extremely luscious set of locks there. So Boyle's Law is something he found. He was investigating the relationship between pressure and volume for a fixed number of moles of gas at a fixed temperature. So basically he kept the same number of moles of gas. Actually, he used a constant mass of the gas, but we now know that that's the same as a constant moles of gas. And he kept the temperature the same, but then he changed the pressure to see what would happen to the volume. And what he found was that the volume was inversely proportional to the pressure exerted on the sample of gas. So we're going to look a little bit about what inversely proportional means. So direct and inverse proportion. A directly proportional relationship is where this symbol here is proportional to. Just means that if X changes, Y changes by the same factor. So Y is equal to some constant term here multiplied by X. And of course, if you have Y equals Kx, or you may have seen this written as Y equals Mx, then you know that that is the equation of a straight line through the origin. Because you know that the equation of a straight line is y equals mx plus c, where c is the y-intercept. But if there's no y-intercept, then we know that the y-intercept, or if there's no value of c, we know the y-intercept is 0, 0. So directly proportional relationships are not only just straight line relationships with increasing gradient, but there's also that condition that they pass through the origin so that we have that particular form of the equation, y equals kx. Now that means as x is increasing, y is increasing, and by the same amount each time, and therefore we get a linear relationship. Inverse proportion, on the other hand, is where if one of the variables is increasing, the other is decreasing. But there's even more to it. That's what an inverse relationship is. But if we're saying it's inversely proportional, then we have y is proportional to 1 over x now. And of course, that means y is equal to k times by 1 over x. And that means that y is equal to k over x. And if you actually graph y versus x for an inversely proportional relationship, you actually end up with a hyperbola for your graph. So this graph here is a hyperbola. All right. So the inversely proportional relationship is not overly useful for us in talking about Boyle's law if we're graphing y versus x. So y versus x gives a hyperbola. But what we are really looking for is a linear relationship. And to do that, we know that y is equal to k times by 1 over x. So to get a straight line relationship there, we're going to need to plot y versus 1 over x. And of course, for Boyle's law, we're not talking about y's and x's, we're talking about volumes and pressure. So for Boyle's law, that would be volume and that would be pressure on the axis. So then we'd have V equals K over P. So for Boyle's law, we want to plot the graph of y versus, y versus 1 on x, which will be V versus 1 over P, if we're looking at Boyle's law. So let's have a look at, if we're actually going to plot that graph, then this axis here, what we usually call the x-axis, is going to be the 1 over x-axis, or it's going to be the 1 over p axis, and this is going to be the v-axis. Okay, so let's have a look at some experimental data. We have here a cylinder containing a gas and a movable piston. So this is our movable piston here. And we're able to actually change the volume of this gas, and up here we have a barometer that's measuring the pressure. Okay, and if we choose, by sliding the piston up and down, we'll do this by screwing this screw, which would move the piston. By doing that, you can get lots of different values for pressure and volume. And here's a sample of results that I found. And you can see if we plot those results, we are getting a hyperbola. When you do this experiment yourself, you're probably not going to be able to plot the correct range of values to get the full hyperbola. But if we do that, we get a hyperbola. If we want to turn that into a straight line graph, we're going to need to plot, instead of this one's volume versus pressure, and that's going to give a hyperbola. But if we do volume versus 1 over pressure, then we should get a linear relationship. And we're hoping that we can get a linear relationship that's actually going to demonstrate proportionality as well. So you can just dump that data into your Excel. I've just here added a p to the minus 1. Of course, p to the minus 1, anything to the minus 1 is 1 over it. So that's our 1 over p there. And we're going to take a graph. If I graph those values there, you'll notice that my axes are V and P to the minus 1. Well, P to the minus 1, and of course, if P is in kilopascals, P to the minus 1 will be in kilopascals to the minus 1. And then if I apply a trend line just to that set of data, then I end up with an equation of a line and an r squared value that I can apply. Now that is not, we actually have a y-intercept here. We've got an excellent r squared value. Remember, r squared or equal to 1 means your data perfectly fits the trend. Here we've got 0.9999, another 9. So this is a pretty good fit. But what if I forced the graphing software to include the 0.00? This is the graph I get. And you can see I still have that excellent r square value. So I'm going to be very happy with that. And what I've got here is an equation of a line, which is y is 6178.8. x, but my y-axis is actually volume, and my x-axis is actually p to the minus 1. So what I've got here is volume is equal to 6,178.8 times by 1 over pressure. And if I do myself a little bit of algebra on that, then I get PV equals 6,178.8. Now this is a constant. So that means for each of these points on the line, they have a volume, a p to the minus 1 coordinate and a v coordinate. And if I plug those into my equation, no matter what values I have, p times by v is going to be equal to 6,178.8. So if I have the first point, first pressure, and the first volume, that's going to be multiplied together, that's going to be equal to 6,178.8. If I took a different set of points, maybe I took those points there, then my pressure times by my volume there, because it's on the same line with that equation, it's still going to be 6,178.8. And suppose I took this point here. A third point, its pressure times by its volume is still going to be 6,178.8. So what we've actually demonstrated here is the mathematical statement of Boyle's law, that no matter which pressure and volume you take, the product is always going to be the same. And that is what Boyle's law says. So mathematically, Boyle's law says for a sample of gas of the same number of moles and the same temperature, if you take any combination, if you put the gas under a certain amount of pressure and measure its volume, and then you put it under a different amount of pressure and measure that volume, you're always going to get this, the product of pressure and volume being the same. And so the mathematical statement is P1V1 equals P2V2. And the nice thing about this is if you know any three of these four, you can calculate the fourth. And that's what we're going to do in some examples in class. That's all for this time. I will see you in the next video.